Okay,
Yes.
so good morning everyone. Assalamualaikum warahmatullahi wabarakatuh. Today we meet again in this analytical dynamics class. By the way, if you have any problem listening to my voice, please let me know, yeah. Either by raising your voice, yeah,
No problem, sir.
verbally, or I don't know, maybe make a chat in this chat column, yeah. Okay, so last time we discussed about any question about last time? So I think we were here, yeah. Last time we discussed about the Newtonian mechanics of a single particle, and then we saw that all the conservation laws, yeah, the conservation law of linear momentum, conservation law of angular momentum, and conservation law of energy, they are all they're all consequences of either there exists external force or not, external torque or not, or whether the force involved is a what do you call conservative or not. Okay, so basically this is things that you have learned in undergraduate. Yeah. Now I'm going to move on to the case for a system of particles. So if previously we discussed about the mechanics of a single particle, now let's consider what if we have a system of particles. By system, I mean a collection of more than one particles. Okay. By the way, can you hear my voice clearly, or should I move closer to
clear.
Okay, thank you. All right, so let me continue. So instead of one single particle, let us imagine that I have, okay, let me just write down the title here. Okay, let me just, oops, sorry. Okay. Today we're going to discuss the mechanics of a system of particles. Okay, now imagine that we have a collection of particles. Let's say I make an isolated area like this. Maybe this is a bag or anything. So what is within this boundary is what I call a system. So the system is denoted by this boundary. So here I have a system of many particles. Let's say that I have this is a particle 1 denoted by it has mass 1, and then it's particle 2, mass 2, particle 3, mass 3, particle 4, mass 4, and so on. Yeah. I can go on. In principle, I can have a number of particles. Okay, I have many numbers of particles.
So these are, excuse me, sir.
Yeah. Yeah.
So these are just like gas particles or a bunch of particles together.
Yeah. Right. So this is the system of particle can system of particles can it can either be discrete or it can be continuous. But when it's continuous, we are going to talk about this the continuous system of particle when we talk about the rigid body. Okay. Well, a continuous system of particles can either be a rigid body or maybe fluid. Yeah, fluid is a system of many degrees of freedom. Like it can consist of many particles, and it's continuous. But we're not going to discuss fluid here. So maybe in this course, when it's about when talk about the continuous system, we are going to discuss it in the dynamics of rigid body. So in general, system of particles can either be discrete or continuous like that. But for the sake of simplicity, let me first start with a discrete system here. So I have n number of particles, and you can count each of them. So that's what I mean by discrete. Does that answer the question?
Yes, yes, sir.
Okay. So yeah, we can consider that we have a system of n particles. Okay. Now each particle experiences a forces. Yeah. So for example, let's take a look at M1. M1 it experiences force, maybe more than one force. So let's say that M1 is applied by an external force, okay, somewhere like this. Okay, let me just. Okay, this is an external force. Yeah. I'm going to call it F1. So F1 is an external force that works on M1. Yeah, I'm going to give a superscript E here to denote that this is an external force in order to distinguish it from a force that is not external. Okay, so M2, M3, and so on can also have they can have external forces applied on them. Okay, so I'm just making a case for M1, but in principle, each and all of them can have external forces as well. Now, what differentiates this system or this condition from our previous discussion is that when we talk about many body or more than one particles, there exists another interaction, right? So when we talk about only one single particle, so we apply a force and that's it, right? That's the only force. I mean, this external force, you can imagine that this is not only one type of force. Yeah, it can be, for example, more than one forces. As long as it's external, I can put them here. So it can it may be like a electric force or Coulomb force, or maybe you can apply a push here, and also many forces. Yeah. So external here, you can imagine that this is the resultant of all of the external forces applied on M1. All right. I don't care where they are from. I don't care what they are individually. As long as they are external, I'm going to put them all under this notation. Okay. Now, besides having external force, our particle can also have. It doesn't have to be, but it can also have. It may have another interaction with the other particles. Yeah, and this is actually what. So a system of particles can either be a collection of particles independent of each other, not interacting, or we can also have a collection of particles interacting with each other. Okay, so in the case of interacting with each other, for example, I have M1 interacts with M2, yeah, as well as M1 interacts with M3, M4, and M5. All right, so from that possibility, I can draw that M1 can have a force toward M2 like this. And this is called, I'm going to call it later, but also it has a force toward M3, right? It has force toward M4, and it has force toward M5. So if it has, in principle, if you have n number of particles, so each particle, let's say for example M1, it can have n minus 1 number of internal forces, right? So each internal forces is going to be, I'm going to call this internal forces, this one that goes to M2, I'm going to call it F, what do you call that? F21, okay? 21 means that the force that the M1 experiences due to the existence of M2. All right, so that's basically the definition of F21. And also M1 can have a force F31 due to M3, yeah, F41 due to M4, and F51 due to M5. All right. Now, reciprocally, the same thing happens, right? M2 can also have interaction with respect to M1, with respect to M3, M4, and M5, and others. So besides having F21, we can also have F12, right? So actually, internal forces. Okay, these are what I call the internal forces. Yeah. The forces that interact between each member of a system. So if this is called F21, then those are called F12. Okay, I'm going to use a different color. This is F12. Yeah, this is F13. This is F15. This is F14, etc. Okay, so you can get what I mean. So for example, I'm just drawing it here again. If this is M1 and this is M2, let's say, yeah. So the force that I draw from M1 to M2 is going to be called okay, just moving the point here. Let's do it here. Yeah. All right, so this is M2, and this purple arrow is what I call F21. Now, reciprocally, I can also have the force that goes from M2 to M1, and this is called the F12. Yeah. So the same thing happens to other member of the system. Okay. So now we know we have two types of forces. Yeah. We have two types of forces. They are two types of forces. The first one is external force or external forces, yeah, because we can have more than one. External forces. I'm going to denote it by this Fi with a subscript E. Okay, so the I here labels which particle we are talking about. So I run from 1 to n, and the E here denotes that this is external. Okay, and also we have internal forces. Now, internal forces can be in several possible forms. Yeah. For example, well, the simplest one, if each particle has mass, so the internal forces between particles is obviously gravitational force. Yeah. So M1 exerts a gravitational force on M2, and so the other way around. M2 exerts gravitational force on M1. So F21 is the gravitational force that M1 experiences due to M2. And so F12 is the gravitational force that M2 experiences due to M1, right? Question? So this internal forces, it has two indices. Yeah, it has two indices, and I will not have any subscript for internal forces. Yeah, because the two indices will be sufficient to label them as internal forces. Now, if you can see here, the internal forces, they are all mutual, right? They are mutual and opposite. So what I mean by mutual and opposite is that uh, the 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 magnitude of the internal forces is the same. Like for example, F21, the magnitude of F21 is the same as the magnitude of F12. Yeah, this is I mean in gravitational force or in Lorentz, sorry, in Coulomb force, these are the case, right? The force
Total force will be
between
zero.
two particles are the same. Yeah, the attractive forces between two particles are the same, right? But the direction is opposite. So mathematically, we can write that Fij is just minus Fji. So if I switch the indices, if I switch the sequence of particles that we are talking about, then the force just switches the direction, but the magnitude is the same. Okay. Right. So basically, this is the first assumption that we take for internal forces. Okay. Obviously, in general, internal force doesn't have to follow this rule. Yeah. This is the rule that we assume. Yeah. And this is a reasonable assumption because in many cases, this is what happens. Like for example, in the gravitational force, this is what happens. In the case of Coulomb force, this is what happens. Yeah. So this is not unreasonable assumption, and so that's why we take it as an assumption here. So this is the first assumption that we take for internal force. What is the other assumption? Well, the other assumption, and this is a bit weaker assumption than this one, but it's still reasonable, is that the internal force is central. In other words, it is proportional to the position vector along the line joining two particles. So I'm going to write down mathematically like this. So what is Rij? Okay, let me just put it here. So suppose that the system lives in 3 dimensions. Yeah. So the suppose the system lives in 3 dimensions. Just put another coordinate here for completeness. Now I'm going to call, let's say this one. I'm going to call this one as R4, right? R4 is the position vector of M4, right? I can put position vector for each of them, yeah. But I'm just going to take one example. So Ri in general, yeah. So Ri in general is the position vector of Mi with respect to the origin. Okay, so R1 is the position vector of M1 with respect to the origin. M3 is the position vector of, sorry, R3 is the position vector of M3 with respect to the origin, etc. Now, what is Rij? Rij, so for example, if I take this example again, this is M1, this is M2, right? Now, from the origin I can take this to be R1, and this is R2. Yeah, this is, sorry. This is R1, this is R2, right? Or maybe I can make it general. I don't have to say it 1 or 2, yeah. I can call it MI and MJ, right? In general, this is what we call. So this is the position vector of Ri, and this is the position vector of, sorry, of Rj. Okay. Now the question is, what is Rij? Well, simply Rij is just the position vector between Mi and Mj, right? So Rij is just let's see. If this is F21, so Rij can be called like this, yeah. This is called sorry, Rij. Rij. So basically, Rij is just from this factorial diagram. Rij is just what? Ri minus Rj. Because Rj plus Rij equals Ri, right? So Rij is just Ri minus Rj. So if I have a vector from I to j, then it's gonna be called Rji. And Rji is just the minus of Rij, okay? And this is just minus of Rji. Is it clear? So now Fij is proportional to Rij in the sense that the direction of Fij is in line with the direction of Rij, okay? And also not only proportional, but the Fij depends only on the radial distance, so the scalar distance of Rij. Okay, so Fij is proportional to this. The direction is along the Rij, and the magnitude of Fij depends only on the scalar distance between I and j. Or in other words, what I mean by scalar here is like this. This is the scalar distance of Mi and Mj. All right, question? Okay, so these are the assumptions that we make in order to simplify the analysis. I should also put that I runs from 1 to up to n. Yeah. Now the total force. What is the total force that it experiences? So the total force, we can focus on M1, let's say. So M1, the total forces that M1 experiences, both from external as well as internal, on Mi in general, yeah, is just I'm going to call it just Fi, yeah. So Fi is just the total force, and this consists of the total external force, right, plus the sum of all internal forces on Mi, okay? And this, so you can imagine that, for example, we have 5 particles. So M1, how many internal forces that it has? It has 4 internal forces, yeah. because it interacts with M2, with M3, with M4, and with M5. So there are 4 internal forces related to M1. The same goes for M2. Yeah, M2 has 4 internal forces. So in general, if I have n number of particles, for each particle, there exists n minus 1 number of internal forces, right? In mathematically, I can write down like this. So I can sum all internal forces, yeah. If M1, so this means that I have Fji. So I have to sum J, yeah. J is sum from 1 to n, but it doesn't include J equals to I. Okay, you get it? So J can run from 1 to n, but it excludes the case or the term where J is equal to I, because F11 is just 0. Yeah, M1. What is the internal force between M1 and itself? Well, it's 0. Okay, so there is no internal force between any particle with themselves. Yeah, with their self. Sorry. All right. So sorry, I cannot see. Can I see? Okay, sorry. Let me just share again. Question? No.
No, sir.
Right. So now, yeah.
It's
No.
clear, sir.
So what I mean by FJI here is just the internal force exerted by jth particle, yeah, jth particle on the ith particle. Okay, so Ji means that J can run from 1 to n, and these are all internal forces work on the ith particle. I can also rewrite this in a more systematic way, yeah. So I don't have to care about the summation of J. J can run from 1 to n, so I don't have to give it's not equal to I, but I can put here 1 minus delta ij. Okay, so you can read this. So what does that mean is that when J is equal to I, this delta, this is delta Kronecker, yeah? You know, delta Kronecker. Delta Kronecker will be 1. So 1 minus 1 is 0. In other words, when J is equal to I, this term is 0. But when J is not equal to I, this term is not 0 because delta becomes 0. So 1 minus 0 is just this one. So this is another way of writing it. All right. Now, having known all the forces, we can ask what is the Newton's law. Remember that for a single particle, the Newton's law is what we discussed, yeah. For a for a system of particles, let's take a look at well, the Newton's law is the same for each particle, yeah. So the Newton's law for sorry for the ith particle, yeah. For the ith particle, this is just the dpi dt, remember, right? So this is the rate of momentum, of linear momentum per unit time. And this is just the summation of all forces involved. And this is the total force. So the total force can be written as the external plus internal, right? 1 minus delta ij fji. Okay. Right. This is a Newton's law for one particle in a system. If I want to calculate if I want to express Newton's law for all particles, right? So for all particles, so I'm going to erase this. Yeah, this is only for the ith particle. Now I'm going to sum them up over I, right? So I'm going to sum them over I from 1 to n. So what does that mean? This means that for each particle they satisfy Newton's law. Now I want to know what is the Newton's law that this whole system satisfies. So I sum them up for all particles. Okay. What would happen here? Well, now take a look at the left-hand side. The left-hand side, since mass is constant, right? Mass is constant, so the dp dt can be written as a d squared dt squared, right? Of what? Of m. Well, I can put m outside, but I can as well put m inside it for m ri, right? Because dp dt is the second derivative of m times ri, because the second derivative of ri with respect to t is just a, the acceleration. Now I have to sum this up, right? Now the right hand side, I can sum this, right? Plus, so I have double sum for the second term on the left hand side. Each runs from 1 to n, right? This is to n. 1 minus delta ij times f ji, right? Okay. Now let's take a look at the right hand side. What is this? This is the sum of all external forces working on a system. Okay. So I'm just going to call. So I run from 1 to 0. Yeah. Sorry, from 1 to n. I mean, there is no bar here. The bar should be on f. Sorry, and it runs from 1 to n. Now I'm just going to call this the total external force. Sorry, so there is no more in the index. So this is just the total external force, right? This is total external force. Now what is this? Can you guess what this is? What is the result of this?
Total internal force.
Sorry?
Total internal force, sir, and maybe I think it will be 0.
Okay, why is it 0?
M1, like if we are saying that F1 2, so there is another force F2 1. So they will cancel out each other.
Right, that's correct. So let's take, for example, I have four particles here. So for each particle, let's say for M1, it exerts M31, right? And M21, M41. Sorry. But equivalently, each particle, each other particle will also exert different forces, right? So this is the force that M1 experiences due to M3, and equivalently there exists force that M3 experiences due to M1, and so this one as well, and so this one as well, yeah. So if I sum them up, so F12, for example, like this. So total here is F12 plus F13 plus F14, and then plus F21 plus F23 plus F24 plus F31 plus F32 plus F34, right? Plus, oops, sorry. Plus F41 plus F42 plus F43, right? In general, they are 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 10, 11, 12. There are 12, sorry, 1, 2, 3, yeah. 1, 2, 3. There are 12 here. Internal forces working on this system of 4 particles. But each cancels out, right? As you can see, F1 cancels with, sorry, F12 cancels with F21, because F12 is just minus F21. F13 cancels with F31, right? F14 cancels with F41. F23 cancels with F32. F24 cancels with F42, and the last one, F34 cancels with F43. So all of them cancel out, yeah. And you can generalize this number to any n number, yeah. In general, since the internal forces are all mutual and opposite, so this term will always be 0, okay. And this is because Fij is minus Fji. All right. So, okay. And then on the left-hand side, I can put this summation inside the derivative, because summation is independent of the derivative. Yeah. So on the left-hand side, I can put down like this. Sum of I. Sorry, this has mi. Mi, ri. On the left-hand side, we are left with only this one. Okay. Right? Okay, now let's consider back the system here. We have 4, let's say that we have 5 particles, but in general we have n number of particles. Now I want to define a point in the system that may or may not lie on one of the particles. So this point that I'm talking about can be on one of the particle, or it can be outside each particle. So for example, in general, the point can be put, I don't know, here. Okay, this point is I'm going to call CM, and CM stands for center of mass. So this is the CM, center of mass. I'm just gonna erase this. And the CM is center of mass. What does center of mass mean? This is it has its own definition, right? So for more than one particles, we can define a center of mass coordinate. So how do we define that? Well, we define that by define what we call the center of mass, CM position. So CM position is denoted by the capital R. The vector position is capital R, and this is defined as the sum of mi times ri. Okay, and then this is divided by the sum of mi, right? So it sounds like the average, not really, not quite the average, but yeah, this is how we define the center of mass. Now the denominator is just the total mass of all particle, yeah. So this is just the sorry, this is just the total mass. I'm going to denote it by capital M. This is total mass, and this is, well, as it is, yeah. I do not have any new name for this. But then you can see that the sum of mi ri, this is just capital M times the center of mass vector. Okay, this is just direct consequence of the definition of a center of mass position. Okay, but now I can put this into the left hand side of the equation above. So what do I have? So I have d squared over dt squared of m r, and this is just f. Sorry, I'm going to put the e in the subscript. What does that mean? Well, since the total mass is also constant, it doesn't change. So that means I have m times the second derivative of the center of mass position. And this is just like this. Well, what is the significance of this equation? Well, if you take a look at this equation, this resembles Newton's law, right? On the left hand side we have mass times the second derivative of position. On the right hand side we have the force. Okay, so what's the difference? The difference is that this is Newton's law, not on any single particle, but this is the Newton law applied on the center of mass position. So what does that imply? So this implies that the system, when we exert the system with external forces, okay, and we don't care about the internal forces of the system. As long as we exert external forces on the system behaves or the system moves in such a way that as if the external force works on one single point, and that point is the center of mass position. Okay, can you get what I mean? So this system, even though it consists of many particles and number of particles, yeah, but once we apply external force on each system, or maybe on some of the members of the system, yeah, it doesn't have to be all of them. Okay, suppose we exert external forces on some particles inside the system moves, or the system behaves in such a way as if the system is like one single particle. And we can what do you call that? We can substitute the many number of external forces working on many members of the system, yeah, as one single external force working on the center of mass. So it is as if that the system behaves in the following ways. This is the system, yeah. This is the system. I don't care how many particles the system has. I don't even care what kind of internal forces working. Yeah, I don't even care how many particles are exerted by external forces and what type of external forces they are. What I care is that some of them are exerted by external force. So I can effectively replace the picture with this. So this arrow represents the total or the external, all the external forces that working on the system. I can replace it with one single arrow, and this cross point denotes the center of mass. So it is as if this whole system is reduced to one single point at center of mass, and the single point is exerted by the external force. So studying the system of particles, we can reduce our picture or our visualization as if that system becomes one single particle again. Okay, so that's nice. Okay. So, all right. Now, well, we can define the total momentum of the system, yeah. Total momentum of the system. Total momentum, just P without any indices. So this is just sum of all P, right? And this is just sum of each individual mass times the Ri dt. Okay, but we know that this is just well, we can see from above that sum of mi times Ri is just m times capital M times capital R. So this is just m times d capital R dt. So this is the total momentum of the system. Now, the direct consequence of this expression of momentum is that if the total external force is zero, well, by zero I mean that all the external forces cancel out, yeah. Then the total linear momentum is conserved. Okay, then the total linear momentum is conserved. And interestingly, this conservation of linear momentum is independent on the internal force. So it is it's okay if you still have internal forces between particle, as long as there is no external forces, then the system has a conserved linear momentum. Okay, so let me put it here. This is just a direct consequence of the definition of total momentum. If the external force is zero, then the linear momentum of the system is conserved. All right. So this is the conservation law of linear momentum for a system of particle. The conclusion the conclusion is the same, right? But the system but the situation is different. If you recall our last meeting, we have the conservation of linear momentum for one single particle. Now we have a conservation of linear momentum for a system of particles. Okay, the situation is different. One is just one single particle, the other is collection of many particles. But the conclusion or the conservation law is the same. Yeah, as long as the external force is zero, then either the system or the one single particle has conserved linear momentum. Okay, question?
No,
Now
sir.
let's move on to another momentum, which is the angular momentum. We already defined the angular momentum last time, yeah?
For single particle.
The angular momentum is defined L. Yeah. So now this is the angular momentum for the ith particle. Yeah. It has Li, right? So this is just the position vector of the ith particle cross the linear momentum of the ith particle. Okay. So for example, I have this m1, m2, m3, so on. Yeah. And I have, suppose, like this. Okay, maybe I'm just putting M2 here. Now, this is R1. Sorry, yeah, this is R1. Okay, now suppose the M1 experiences, well, it has velocity, yeah, and the direction of the velocity is arbitrary. So suppose that it has velocity along this direction. Okay, that's velocity. Let's call it v1. So since it has velocity, it has momentum along this direction, right? So this gives you the p1. Now we can calculate the angular momentum of m1. So this is given by r1 cross p1. Now, if I want to calculate the total angular momentum, yeah, so this is just summing over I for all Li, right? And this is just written like this, Ri cross Pi. Okay. So I'm not going to write down this n all the time, yeah. I'm just going to sum over I, yeah. And unless otherwise stated, you can assume that the summation is always for all n, up to n. Okay, unless I state explicitly otherwise. Oops, sorry. Where is my 3, 4? Okay, 3, 4, 5. Okay. Right. So now, well, we can also calculate the. Remember that the torque, yeah. We have the torque. Torque. What did I use for the torque? Oh, N. I used the symbol N for the torque. So the torque N, right? This is defined to be, so the Ni, the torque on each particle is given by Ri cross, let's call it the Pi dot. Yeah, this is just the force, yeah, working on Mi. And the force can be everything, can be external force and can be internal force, okay? Now, if I'm calculating this torque for Mi, what do I get? So I'm crossing Ri with, what is Pi dot? Well, Pi dot is just this one, right? Pi dot. So this is Fi external plus sum over J of 1 minus delta ij fji, right? Let's just put it like this. Right, so this is the torque for one particle, yeah. So the n for one particle is like this. Now I'm interested in calculating the total torque the system experiences. So that means the total torque is just n without any index. So this means I'm summing over I, right? And this is just sorry, what do I do? What did I do? Right. So basically the left hand side, so here, right, I have Ri cross Pi dot, right, and the right hand side is just Ri cross Fi of E plus sum of j 1 minus delta ij. This is Ri cross Fji, right? So this is just what it means. Now I'm going to sum them over I, right? So the left hand side and the right hand side can be as follows. Take a look at the left hand side first. The Pi dot can be written as like this. D dt of mi times vi, right? Vi is just Ri dot. So this is the left hand side. Now the right hand side, we have sum of I, Ri cross Fi of E plus sum of I and sum of j, sum of I and sum of j times 1 minus delta ij times Ri cross Fji. All right. Question?
No, sir.
Oh, sir.
Now let's take a look at the left hand side. The left hand side, we know that we can write down this the equations inside the parenthesis as Ri, sorry, as the total derivative, total derivative of Ri cross mivi, right, minus, right, mi, I can pull mi out, and this is just Ri, sorry, dri dt cross vi, right? So this term can be written as these two terms. But what is dr dt? Dr dt is just vi. So vi cross vi is 0. So the second term is 0. Okay. Second term is 0. Now take a look at the right hand side. What is this? What is this? Okay, this is a bit difficult to see clearly. It may not be a what I call the intuitive, yeah. But I can imagine, like for example, I have okay. Let's take an example of three particles. Yeah, and you can always generalize to a number of particles. So I have three particles. Each particle has its own position vector. Yeah, M1 has R1, M2 has R2, M3 has R3. Now, when you want to calculate this, what does that mean? It means that you run I and j, each of I and each of j from 1 to n, right? So I have, for example, here, if you run, you will have like this, 1 minus delta 1, 1, R1 cross F. Well, we can immediately exclude the case for I equals j, yeah, because this will be 0, so I don't have to put them in the calculation. So the cases where I is not equal to j, then this 1 minus delta ij always give us 1. So here we have R1 cross F21, okay, plus R1 cross F31, okay, those so much for I equals 1, plus R2 cross F12, right, plus R2 cross F32, right, and we have R3 cross F13 plus R3 cross F23. So you can see what happens here immediately. We have six, for three particles, we have six terms for this part, yeah. But then we know that F21 is just minus F12. F31 is just minus F13, and F32 is just minus F23. So this is reduced to like this, R1 minus R2 cross F12, let's say, right? Because this comes from the first and the third term, right? Plus this minus this cross F1, sorry, this minus this cross F13 plus this minus this plus cross F23. So in principle, this whole thing can always be reduced to be like this. It can always be reduced to be Ri minus Rj, right, cross Fij or Ji, the same, yeah. Okay, let's put it, let's put Ji, yeah. Let's be consistent. So here Rj minus Ri cross Fji, right? And this is summed over ing. Okay, so basically this goes like this, yeah. This is proportional to like this, okay. But we know that this is just Rji, right? This is just Rji. So we have Rji cross Fji. And what is the result then? Rji cross Fji. What is the result?
0, 0.
Why?
Because it's parallel to each other.
Exactly, because the direction of Fji is along the direction of Rji, right? So this is the assumption. Sorry, I put this should be like this too, yeah. Okay, so we have two assumptions about the internal forces, and that follows that assumption. So this should be 0 because the direction is the same, so the cross product is 0. All right, so this whole thing is 0. So on the right hand side, we are left with this term, and on the left hand side, we are left with this term. Okay. Question? So now I can write down that the left hand side, yeah, we can see that this is just Ri cross d. Sorry, I'm here. What I'm saying is here. Yeah. Ri cross MIVI. MIVI is just PI. So this is Ri cross PI. And we know that that is just the definition of momentum. Yeah. Ri cross PI is just Li. So the left-hand side is just the right. I have to put summation. I'm going to put summation outside like this. So this is just the angular momentum of the ith particle, and the right hand side is just the, well, you can write down like this, Ri cross F of E I, yeah. So the left hand side, I can put the summation out inside, so this becomes L, the total linear angular momentum, and this is nothing but the total external torque. Okay, so this is the relation that I get. Okay, as before, at first it looks simple and it looks trivial because this is the relation that we got for the single particle. But then this is not a single particle system. This is a system of particles, more than one particle. But the equation of motion somehow still obeys the same format. Now, the direct consequence of this equation is that if the external torque is 0, then the angular momentum of the system is constant. And this is what we call the conservation law of angular momentum for the system of particles. You see here that the conservation of angular momentum doesn't depend on the internal torque. Okay, so it may be that the system has internal torques, yeah, between particles, but we don't care because as long as the external torque is 0, then the system has a conserved angular momentum. Okay. Right now, last time before I end this class, yeah. By the way, for this week we're going to continue on Friday. Yeah? Okay, let's see. Maybe on Friday we can still have online, yeah, and we can start the offline class starting Monday. Okay. So now, imagine that. Okay, this is the origin. Yeah. Let's take, for example, this is the particle 1, yeah, or the ith particle, yeah, and this is the position vector. Now I have other number of particles. Yeah, I have number of particles, but suppose that I don't care about them. I just want to care about this center of mass position. Okay, so this is the center of mass position. This is the CM. Yeah. So this is called the capital R. So I will define now the position vector from the center of mass to the MI is given by Ri prime. Okay, so Ri is position vector of Mi from the origin. Yeah, capital R is the position vector of the center of mass from the origin, and the Ri prime is the position vector of Mi from center of mass. Okay, so you can easily see that the Ri prime, yeah, the Ri prime is simply Ri minus capital R. Okay, now if I'm taking or equivalently, this is saying that Ri is just Ri prime plus capital R. So if I'm taking the derivative of this, I get the Ri dot, which is the Vi. This is just the Ri prime dot plus R dot, capital R dot. Okay, I'm going to write down like this. This is just the Vi prime plus capital V. Okay, capital V is just d capital R over dt. So what is this? This is the velocity. Vi prime is the velocity of Mi with respect to the center of mass, and capital V is just the velocity of the center of mass with respect to the origin. And the origin is always be arbitrary. Okay, we can always take any point as the origin. So what do I want to do? I want to calculate the total angular momentum of the system. Yeah, so I'm calculating L. L is just the sum of I, Li. And this is just Ri cross Pi, right? But now, Ri can be written like this. Okay? And Pi is just Mi times Vi. So Vi, by the way, this is Vi. Yeah? This is Vi is equal to Vi prime plus capital V. So I can write down this whole thing as the Ri can be written as Ri prime plus capital R, right? Cross, what is Pi? Pi is just Mi. I can pull Mi out. And this is just Vi. Vi is just Vi prime plus capital V. All right, so we can write them down explicitly. I just need more space here, maybe. So this is I. So what are they? Just write them down individually. Yeah. So this is Ri prime cross Mi Vi prime. Okay, this is one. This is first term. What else? Ri summation of. Okay, maybe the sum should be outside there in order not to. So this is the sum. like this. So I'm going to do the same thing here. Sum of what? Of Ri prime cross Mi times capital V plus what else? Capital R cross Mi Vi prime, and the last one is a capital R cross Mi Vi. Oh, capital V, I mean, sorry. All right, so this is all of them. All right, so I'm just going to write down, take a look at the last term. So this, the sum is just on Mi because capital R and capital V they do not depend on the index. Yeah. So this can be written as R cross sum of I over like this times capital V. And this is just capital M, right? So this is R across MV. Capital R cross capital M times capital V. Okay. What else can we see? Okay, now let's take a look at this. So this is basically summation of I of what? Mi Ri prime, right? And this is cross with V. I should put V here, right? And how about this? This one, well, this one is also similar. Yeah? This is R cross sum of Mi Vi prime. Okay, let's take a look what is summation of Mi Ri prime is. Well, we know the definition of center of mass, right? What is the definition of center of mass? R is just sum of Mi Ri over capital M. Okay. Now we have this. Let's calculate the summation of Mi times Ri prime. Well, we know Ri prime, so this is just Ri. What is Ri prime? Ri minus R, capital R. All right. But what is this? So this is just sum of Mi times Ri minus sum of Mi times capital R. Well, this is just capital M times R. And from the definition of here, we can see that capital M times capital R is just Mi Ri sum over. So if I have this minus that, this is just the same as this minus that, and this gives you 0. Okay. So this Mi Ri prime summed over I is just 0. Question? So this is just 0. How about this? Well, we know that this is Mi dRi prime dt. This is sum over I. And once again, we can pull this dt out of the summation and we will get the same result. So this also be 0. So these two terms are 0. So we are left with the first and the fourth term. Okay. So what do I get here? L is just the sum of Ri prime cross pi prime. What is pi prime? This is ri prime cross, this is pi prime, okay? And so this is plus capital R cross capital M times capital V. So this is the total angular momentum of the system. All right, let's dissect what are they. So the total angular momentum are about a point O, yeah. So this is total L with respect to the point O. What is this? What is the first term? This, what is this?
This is the length between the center of mass.
Yeah, as you can see, this is the angular momentum. But the angular momentum of what? This is the angular momentum of the particle of each of total angular momentum of all particles with respect to the cm. So this is total L about around the cm. Okay, why? Because can you see from the diagram here, right? So the angular momentum of mi with respect to cm, because the arm of the angular arm is just ri prime. Okay, and what is this? Capital R cross m, capital M, capital V. This is the angular momentum of cm itself, yeah, about the origin. So the total angular momentum of the system around the origin is the sum of total angular momentum for all particles around the center of mass plus the angular momentum of the center of mass itself. Okay. All right. Any question? I'm going to stop here, and I'm going to continue on Friday. I hope by Friday we can we are done discussing about the Newtonian mechanics.
Sir, Friday class will be on campus.
Let's make it online. Yeah, let's make it online first. Even though active will come, yeah. But let's start the off-campus. Sorry, let's start the offline class on Monday. Yeah. Sorry, next week. I mean, on Wednesday.
Okay.
Wait. What date is next week? Right, Wednesday. Okay, I think next Wednesday. I will not be in the Department of Physics. I have something to do in the University of Indonesia itself. So let's have a class on Monday and Friday next week. Okay.
Okay.
All right. If there's no question, I'm going to stop sharing. So let's meet again on Friday at the same time. Okay. Oh no, maybe on Friday we can have it on we can start at 9:30. So because we can we want to prepare for the Jummah prayer. Yeah.
Yes, sir.
All right. I'm going to stop recording.